Well, good morning. I'm thrilled to be able to take part in this meeting. The N.I.C.E conference is one that I'm particularly fond of. And I'm also delighted that this is part of the IUPAC family of conferences. What I'd like to do today is tell you about an area of research that my group has been investigating for a number of years. And that involves the creation of coatings that resist fouling. It's a perfectly natural biological process, but one that really is undesirable. And the work I'm going to describe has been done by Amanda Leonardi, who recently graduated, and her predecessor, Brandon Wenning. So before I go any further, though, I have to acknowledge long-term support from the Office of Naval Research and collaboration with the groups of Professors Rachel Segelman at the University of California at Santa Barbara, and the group of Tony Clare at the University of Newcastle with associates John Finley and Nick Aldred. Nick recently finished up a long-time postdoctoral stay, and he's now become a professor at the University of Essex. So without these folks, we wouldn't have been able to carry out these studies, as they did a lot of the bioassay work. Now, I mentioned that biofouling is natural, but it is very undesirable. If you go out to the English Promenade in Nice and you look over on structures that are in the water, you'll probably see them covered with seaweed and other types of marine organisms. If that growth occurs on a ship that's trying to move through the water, the presence of the plants and animals on that surface increase drag, and in a very severe case, may even impede the operation of the ship. So today we have really an environmental dilemma. If we leave the foulant on the ship, again, very natural, that increases fuel costs, and that extra fuel consumption per ship could be several $1 million a year in additional cost. Plus, that's perhaps $5 million of fuel that's simply turned into CO2. It doesn't do anything else. So we end up polluting the air. On the other hand, today's coatings involve toxicants, often copper. And if we use that to remove or prevent the fouling, then then we're challenged with the fact that copper can accumulate in the environment. So the process itself involves a number of steps. Immediately on placing an object in a living body of water like an ocean or a sea, bacteria and biomacromolecules contact the surface and immediately start to change it. And then on that, more advanced organisms, perhaps diatoms and microalgae, start to grow. And eventually the more complicated foulers we see in these photographs, such as invertebrates or large-scale algae. And so our goal is to design a surface that can interrupt the process, or alternatively prevent the strong adhesion from taking place, and then simply moving the object through the water will be useful in removing the foulant. Now, this is a situation that's been known for a long, long time. Back in the 60s at the Naval Research Lab, Bayer and Zisman worked together. They studied bacteria growing on surfaces. And what they were able to show was that in the range of about 20 millinewtons per meter, fouling release took place. These are non-polar surfaces, generally silicones and fluorinated materials. And at higher surface energies, higher surface tensions, anti-fouling behavior took place, and these were often more hydrogel-like surfaces. They made no study of the mechanical properties of the materials. And over time, people have come to understand that controlled surface composition is very important, But in addition, the most fouling resistant surfaces are typically an elastomer or the hydrogel, and they have a very dynamic surface. So on this basis, we've been looking at designing surfaces that resist fouling, but at the same time, really trying to come to a much more effective solution against the hard foulers. And we've been doing that by looking at a variety of polymer brushes. Brushes are wonderful materials for interfacing with interfacing a surface with the living world. The surfaces, brush surfaces tend to be dynamic, and you can design them with a wide variety of chemical and structural architectures. And in a work that we carried out some years ago, we were able to show that polymer brushes were extremely effective in preventing the attachment of cells to surfaces. At the time, we did a comparison with self-assembled monolayers and found that in our hands, the brushes were frankly outstanding. And you didn't really need to use very complicated architectures in order to be successful. Now, so what I'd like to talk about in the remainder of my presentation are how we have explored the world of polymer brushes, but how we've developed a strategy that allows us to build a polymer brush-like architecture on a coating that could, in fact, cover a ship. So one of the challenges, of course, is that essentially all the work in the literature on polymer brushes is done on surfaces that were modified in a round bottom flask, and we're not going to be able to put a ship in a round bottom flask or a bottle or any other type of container. We need to develop a coating that provides all the benefits of a brush, but can be applied externally. And brushes grown on surfaces have an architecture that enables basically the polymer chains to extend from the surface. And so that's what we're trying to produce. Frankly, perhaps the most practical approach to this, to developing this kind of architecture, is to build a loose polymer network. But for our purposes, as carrying out fundamental studies, we found that the use of blockopolymers, their ease of attachment and their ability to form physical crosslinks are extremely effective in letting us test different brush types of architectures. We first demonstrated that with an amphiphilic material, a combined fluoroalkyl and PEG unit that had both polar and nonpolar function, was very dynamic. And we were able to show that against species that like to settle on polar surfaces and species that like to settle on non-polar surfaces, that with an amphiphilic surface, we were able to get effective fouling release of both of these types of fouling species. And in this photograph, A and B are, B is a treated surface with this amphiphilic coating, A is a glass slide, and C and D are the same samples that have been subjected to a very fast jet of water. And with the amphiphilic coating, we were able to remove this foulant, in this case, ulva, and on the glass slide, the foulant was retained. So amphiphilic coatings are very effective. Finally, by way of background, we've adopted this small sample technique and developed a method for coating glass slides using this blockcopolymer system. And so what we do is we first salinize the surface with an amine. We use a commercially available thermoplastic elastomer that incorporates anhydride groups. And so we can chemically bind a layer of blockcopolymer on the surface. We coat a thicker layer, and the glassy phase of the thermoplastic elastomer interlocks. And then finally on top, we put a surface active block copolymer. The only requirement being that it has to have a common styrene anchor block. And then we can build a material that's elastomeric and easily easily modified in terms of surface composition. So we have carried out an extensive range of studies, and over time we focused on silicone types of materials. There's a wide variety of means and architectures for producing an amphiphilic polymer with silicones. And we've identified those sorts of structures with PDMS as the backbone, and incorporation generally of polar groups as the side chains as a good means for introducing this amphiphilicity. So if we look at a block copolymer with PDMS, and we use thiol-ene click chemistry to modify the PDMS backbone with, in this case, a PEG unit, we can use anionic polymerization to create either a diblock or a triblock material, and then make this amphiphilic PDMS block. We, as a result, can also use diblocks or triblocks or mixed structures to modify the surface. And we've done that, and you see, I hope in this short video clip, a series of barnacles, in this case a barnacle cyprid, lying on the surface, trying to figure out what it's doing there. And barnacles that have the shape generally of a conical shape, kind of like a volcano. But the reason they're swimming around is actually they're feeding flagella are causing them to move because, in fact, they are not attached. This particular coating is very, very good at resisting fouling. But over time, if you push and force them to attempt to reattach, the biology allows them to change their adhesive, become much more effective, and eventually they do stick. So we're close, but we're not quite there. And what we think we need is an additional strategy for making these materials resistant to hard foulers. And so we've been trying to expand our toolbox between the PEG unit and the PDMS as an amphiphilic material and incorporate other functionality. So we're looking at alternative hydrophilic groups, alternative amphiphilic groups. But today what I want to do is talk about some active groups that we're introducing. And these are radical inhibitors. And the reason we're interested in them is because so many of the hard foulers cure their adhesives through an oxidation mechanism. Some oxidize DOPA, some oxidize disulfides. Other types of chemistry also can be cured. And so it's the cross-linking that makes the adhesive robust. And if we can prevent that, inhibit it, we will always have a soft, uncured adhesive that motion through the water may be able to then dislodge the hard fouler. And so our goal then, as you can see in this figure, is so that when the barnacle tries to put down its radical containing adhesive, our tempo units interfere with that, and we form a very thin layer where attachment is quite weak. Now, we have studied tempo in a wide variety of polymer architectures. Here you see a polystyrene PTMA, the dye block. In our initial study, we had the material, we wanted to incorporate it with our anti-fouling coating. We looked at polystyrene PDMS and polystyrene with PEG modified PDMS. And what we found is that this polystyrene tempo methacrylate block copolymer is an awful material. It's brittle, it's rigid, it cracks. And so we can incorporate it in our coating, but to get it to populate the surface, we have to use it at such a high concentration that the materials really didn't behave well enough to be a long active coating. So our next choice was to take PDMS and modify the backbone with tempo. We used a variety of the thiolene click chemistry I described before, and then we activate an acid with a succinimide group, and then we can incorporate or attach an amine functionalized tempo and incorporate that into the backbone. And the chemistry works well. We end up producing a polymer that has the notable orange color of the tempo unit. And we combined it with a second amphiphilic polymer in order to produce a coating. And so what we learned there was that as we incorporated more of the tempo group and blended it with the PEG material, really the barnacle was quite happy to sit on the surface. And that was very perplexing because we knew that the tempo would be interfering with the curing of the adhesive. And what we eventually realized was that the PDMS is very, very nonpolar. We knew that. The tempo itself is also extremely nonpolar, although it has a number of polarizable elements in the structure. The presence of the 4 methyl groups to shield the stable radical group makes it very, very nonpolar. And so in the coating process, the PDMS and the tempo are competing for that low energy surface, and the PDMS always wins. And so it becomes buried. You don't see the nitrogen that's characteristic of this structure in the final material. And if you zoom in, you can also see that if you incorporate PEG as an additional component in a second block copolymer, in the presence of water, the PEG goes to the surface. And so in neither situation does the tempo win out. And so we have to be more sophisticated in the way we design these components. And what we need to do is to avoid the situation we have where the tempo is buried by the PDMS when we coat it in air, and the tempo is buried by the PEG when we expose it to water. So if we, ultimately we had to do the harder synthesis that we were clearly trying to avoid and incorporate both PEG and tempo on the same PDMS backbone. Clearly we have the same thiolene click chemistry that we can use, and we employed it. And we can also make both the diblock and the triblock copolymer. So we can vary the ratios, we can control overall composition. And again, the styrene acts as an anchor block or anchor segment in our multi-layer structure. So if we look at coatings of these materials, indeed, tempo goes to the surface. So the PEG drags the tempo to the surface, whether it wants to be there or not, after exposure to an aqueous environment. And if we look at the surface composition in terms of what we might expect from the theoretical point of view, and the effect of the dry state or soaked in water, we see that PEG is still competing with the tempo, but because they're in close proximity to each other, wherever the PEG is going, it's dragging along some of the tempo. And arguably, it's close enough to the surface region that it's still going to have an effect on the on any type of chemistry that's occurring in that region. So PEG draws it to the surface, and it stays there, and we believe it's accessible. So in fact, if we look at barnacle fouling and release, we find that PEG is helpful. And if we look at the tempo PEG combination, we see that partnership is very effective in even inhibiting the settlement, but also enabling release. So any material, any cyprid that tries to settle and grow there has a hard time doing it, but any that's there is weakly attached. Now, we also know that the higher the PEG, the better and more effective this is going to be. And so if we follow the growth cycle, we see that both cyprids and the barnacles are inhibited by different systems. So the cyprid settlement is inhibited just by PEG, but the metamorphosed material really can't find purchase on the surface. And the tempo is proving to be very effective. So if we look at this in terms of the number of settled cyprids, we find similar results. The bottom line is we want to have as much PEG in this composition as possible. But one of the challenges is that the PEG increases the solubility or the ability to be washed off. And so we have, again, this balancing act that we have to carry out. And the natural strategy would be to go from the di block, which has one linking point, to a tri block that has two. So we have prepared these materials, and we have begun a study of these systems. We know that they attach and form a much more robust, stable coating in water. And if we look at Ovalinza, one of our seaweed, one of our algae test structures, we find that we have a reasonable response to removal of this. So we're getting the effect that we would anticipate from an amphiphilic material. But as you can imagine, this work was started in December and January of December of last year and January of this year. And in Ithaca, New York, COVID hit. And shortly after that, it hit our collaborators at the University of Newcastle, who had just finished carrying out this work and were logically then going to do the barnacle studies. So in order to find out how well the ABA tri-blocks work, and I'm quite confident they're going to show very nice results, you'll have to come back sometime in the future. So, but let me try to summarize. You can see we've had to march through different architectures. We've done this because the tempo itself is extremely hydrophobic, and yet we have to introduce its wonderful functionality into the surface region. And when you do that by coupling PEG and tempo together in the same component, the more PEG, the better, but we need to build a robust coating. And so we need to use an ABA tri-block material. The co-attached, the combined tempo PEG coatings are excellent fouling release materials, and they can and do inhibit settlement for barnacles and do a very good job at the higher ratios of PEG. And the tempo does not play a detrimental role in the biofilm formation in algal species, but the increased hydrophilic component helps out. So with that, I think I've come to the end of my time. Again, I want to thank the organizers for letting me take part in this. If you have any questions, feel free to email me at ck03@cornell.edu. If I get them when I wake up, I'll try to respond right away. And I'm looking forward to hearing from you all. So thanks very much, and enjoy the conference. I wish I was there with you.